India's formal protected area network relies on a vast, rigidly defined grid, encompassing 573 IUCN Category 4 wildlife sanctuaries, designated as strict safe zones. While expansive, it covers approximately 123,700 square kilometers, equating to 3.76% of the country's total landmass. Overlaid onto this fraction of land are highly specialized zones, including 53 tiger reserves and 33 elephant reserves. The traditional conservation model relies on a clear spatial separation: designate a border, contain the wildlife inside it, and keep human development out. But that rigid zoning faces immediate physical pressure. India's landscape is shared with over 1.3 billion people, driving dense agricultural and infrastructural expansion right up to the edges of these reserves. Simultaneously, the ecosystem within supports immense biological density, including more than 60% of the world's wild Asian elephants. Moving to higher altitudes, the region also holds over 70% of the potential global range for the snow leopard. Apex, highly mobile species require massive grazing tracts and hunting territories. They naturally ignore administrative lines, making static geographical borders difficult to enforce. This chart tracks mortality from 2009 to 2024, revealing the cost of static boundaries. Data logs 7,868 human fatalities from elephant encounters, averaging 500 annually. Over the same timeframe, records show 1,653 elephant deaths resulting from human interaction. These animals are dying from specific anthropogenic causes: electrocution from exposed power lines, high-speed train collisions, targeted poaching, and retaliatory poisoning. These fatalities are escalating, even though the Asian elephant holds the highest level of legal conservation status, Schedule 1 under the Wildlife Protection Act. A spatial analysis of the data shows this conflict is not distributed evenly. 70% of all incidents are concentrated in just 4 states: Odisha, Jharkhand, West Bengal, and Assam. This intense geographical concentration indicates that human-wildlife conflict is structurally driven by specific spatial friction, requiring dynamic intervention rather than passive boundary enforcement. To build a dynamic response, researchers first need accurate population data. Between 2019 and 2023, India conducted the SPAI, the Snow Leopard Population Assessment in India. It was the first systematic scientific attempt to map this highly elusive species across a contiguous range. The survey analyzed approximately 120,000 square kilometers of high-altitude Himalayan habitat. Wildlife biologists utilized a rigorous 2-stage framework to calculate species density. Stage 1 used occupancy-based sampling. Survey teams walked 13,450 kilometers of transects to map zones of probable occupancy. Stage 2 applied abundance estimation. Researchers deployed camera traps at 1,971 locations to capture distinct individuals. By mathematically modeling the camera trap hits against the spatial grid, the SPAI generated a total estimated population of 718 snow leopards. The SPAI framework proves that contiguous, low-friction habitats can be accurately mapped, providing the foundational spatial data required for large-scale carnivore management. Applying spatial ecology to the human-dominated forests of states like Chhattisgarh and Jharkhand requires measuring a different variable: fragmentation. To track this, researchers use land use land cover mapping, or LULC. By analyzing satellite imagery at 5-year intervals from 2000 to 2024, they map exactly how agriculture and built-up areas consume the forest. The satellite data reveals that total forest loss is less predictive of human-wildlife conflict than the fragmentation of the habitat that remains. A large, intact forest ecosystem operates very differently than a forest area fractured into dozens of isolated, disconnected patches. Researchers calculate 2 metrics: patch density, which counts isolated blocks, and edge density, measuring the boundary where forest meets human development. They evaluate these using a 7-kilometer moving window, representing an elephant herd's average daily movement, swept across the map to scan for bottlenecks. High edge density means migrating elephants are forced to constantly cross through farms and highways to reach the next patch of forest. This makes fragmentation a direct catalyst for fatal encounters. To translate that fragmented landscape into actionable intelligence, data scientists rely on a statistical framework known as Generalized Linear Modeling, or GLM. The GLM processes historical conflict using binary code. Actual mortality coordinates are coded as 1. The software then generates random pseudo-absence locations, coding them as 0. To ensure data independence, it deletes any 0 point within a 1-kilometer radius of a mortality incident. Researchers then overlay 12 explanatory variables onto this matrix, calculating the exact distance from each point to croplands, roads, railways, and active mining operations. The results identify intersecting linear infrastructure, like railways cutting through migration routes, or power lines hanging low over fields, as the primary statistical trigger for mortality. The generalized linear model isolates the environmental frictions that generate conflict, identifying the exact coordinates where encounters are mathematically likely to occur. Predictive data only works if ground-level policies adapt to it. A recent survey analyzed the perspectives of 428 frontline stakeholders, including forest managers and researchers, across 33 different elephant reserves. Structural top-down barriers cannot solve fluid spatial problems. Mitigation must match the specific ecological heterogeneity of the landscape to be effective. Relying on static geographical zoning, simply drawing lines on a map to create sanctuaries, fails to account for the spatial requirements of highly mobile species. The SPAI assessment proved we can map elusive populations, and generalized linear models show we can predict where conflicts will occur. This data must now be embedded into decentralized land use planning to restore connectivity between isolated sanctuaries, establishing data-driven corridors for safe migration. Implementing these adaptive, technology-driven strategies is the only path to minimizing mortality for both humans and keystone species. Modern conservation requires engineering safe, data-driven coexistence through dynamic land use planning in a human-dominated world.